The first area of research is essentially building systems, integrated systems with emerging devices. And if you look at integrated systems today, there's two key components. One is a switch, which is today a transistor, and another one is a transport mechanism, which is an electrical wire or copper wire. And with emerging devices, we need to attempt to replace both because both have issues in modern technology. And so on one hand, what we're using as a switch replacement is the electromechanical relay, which when actuated, essentially, or deactuated, cuts off the leakage current that solves some issues in the transistors. On the other hand, as a transport mechanism, we're researching how photonics can be brought in so that now chips communicate within themselves and with each other with photons instead of electrons. That gives us a lot of energy and bandwidth density advantages, of which I'll mention a few. But basically, these two kinds of devices, if they can be brought into the integrated systems in an efficient way, we'll be able to enable decades of very nice, low energy, powerful computing that we're all expecting. So if you look at the switches, the big culprit of today's CMOS technology is that even when you try to turn off the device to do nothing, it's essentially leaking current. And with billions of devices sitting on chips today and our capability to integrate them, what happens is when you don't have any tasks going on, the devices are still consuming a lot of power and there's no way for you to shut them down. And that limits our ability to integrate more and more devices on a given piece of silicon because eventually it will evaporate because of all the power that sits there. Having the technology that can actually turn itself off and not consume any energy when it's completely off is advantageous because then you can have many, many devices on and then turn them on at any point in time when you have them do some computation. But when they're not doing anything, they don't burn any power. And this relay technology allows that to happen. Unfortunately, if you look at the switch, it's very slow. And on its own, it doesn't stand ground to CMOS at all. But what we realized is a collection of these devices that tries to perform a function just like a collection of CMOS transistors, if done and connected in smart ways, can actually compete pretty nicely with CMOS. It just changes the way you engineer these devices and sort of brings out this importance of looking at potential new technology candidates from the circuits and systems level as well, while you're developing sort of the basic device concepts. In fact, that helps you sort of feed back to the device designers which parameters are actually useful in their design. Because there's a lot of degrees of freedom they can use and they don't necessarily know which one is the most valuable to a circuit or a system designer. And we help them guide or navigate this maze of choices they need to make at a technological level to evolve their device to something that will be very useful. So another example is this silicon photonic technology, where there's a number of universities out there in the field, this is about 10, 15 years old, who started, once the phenomenon was noticed, started building photonic components like modulators and filters, waveguides, all sorts of things you would see in normal fiber communication community on chips integrated. And this represented a huge advancement for optics because all of a sudden you could print everything just like in CMOS technology and you don't need to put it together with discrete components, which is very costly. Once you started printing, it's very cheap to produce very sophisticated photonic systems. Now, the slight problem was that you could do it, but you cannot easily integrate it with CMOS transistors. And because people fine-tune the photonic device processes, so they're just so slightly incompatible with what mainstream foundries are doing. And if you look at the landscape there, the whole CMOS production is consolidating in a few big giants. You have Intel foundries on one side, you have TSMC and Asian foundries on the other side, and IMEC, for example, in Europe. And these are sort of the colossal infrastructure organizations where a lot of investment and NRE has been put into to invest in these fabs, billions of dollars for one foundry to start running. So they're very unlikely to change the way they operate for this, even this new and exciting technology. The much better way to fit in and demonstrate the potential is to understand how to fit in their existing recipes and try to leverage the richness of their process. And if you can fit in a photonic device there, even if subpar with respect to what you'd be able to build in your own kitchen, that's cool, you would still be able to showcase the system level advantages of the technology. And this is really what we decided to do, together with Rajiv Ram here at MIT, and now Mike Watts, Miloš Popović also at Boulder now, that we put together a team of people that would try to showcase that indeed in a given transistor process, in fact, the state-of-the-art cutting-edge process like IBM's 45 nanometer technology where you build cell processor and PlayStation game consoles out of Power 7 supercomputers, etc. Within that same technology, you can actually now integrate photonic devices right next to a CMOS transistor and get really high-speed photonic links working and enable a whole generation of systems built, computer systems, chips, communication systems built on this technology with zero changes in the process, and therefore very, very appealing to people to start considering it as a serious contender to the electrical alternatives.